Hey, what's up guys? This is Dr. Vivek Palipuram. In this lecturette, I'm going to demonstrate how to use the R software to perform simple linear regression analysis. Now, in this lecturette, I'm going to use problem number 14.1, where a political scientist would like to determine the relationship between the percentage of voters with the expenditures performed while advertisements. So let's start working on that problem. So first things first, step number one is to read in the data. So I'm going to read in the data vote versus ad.csv. So A is equal to read.csv. I'm going to read the vote versus ad.csv data, and that's my data. So this is the data that I have just read in. In this data, vote is my dependent variable and TV is TV exp is an independent variable, and I need to devise a relationship between them. So first things first, I'm going to read in these variables in my own variable into my own variable. So vote is equal to that, and similarly TV exp is equal to $TV exp. Step number two is to plot a relationship between the dependent variable and the independent variable. So I'm going to do a plot. My independent variable is TV exp. My dependent variable is vote. I'm going to give an X label as advertisements. My Y label is vote percentage, and my main title of this plot is going to be ad versus vote. You can provide your own labels depending on user friendliness. So that's the plot. So this is the plot that has been generated for AD versus vote, and I can find here, or I can see here, that a simple linear relationship will do a very good job in fitting the model, or fitting the data, or explaining the data. So I'm going to fit a simple linear model, and I can use the lm function for that. So lmfit is equal to lm vote is a simple linear function of TV expenditure. Next, I would first identify the summary of this linear fit, and this is the summary. Now, before you go ahead and start using this model, there are some important aspects to look into. The first things first, the values of the regression coefficients beta naught and beta 1. So this is the value of beta naught, which is 2.17, and this is which is the intercept, and this is the value 1.17696 is the value of the slope. Notice the probability values for these estimates to be 0. So the probability that beta naught is equal to 0 is 0.5. It's quite high. So this tells me, in fact, that intercept will not do a good job in helping this model. And looking at the data, it kind of makes sense, because the simple linear line that we are going to fit here, it has a good chance of passing through the origin. So intercept here is not significant. However, the slope here is quite significant. The probability that the slope is equal to 0 is this very small value right here. So it tells me that I should definitely consider slope in my linear model. The last thing that you're going to identify before accepting this model is the multiple R squared value. So the multiple R squared value is 9.91, which tells you that this model explains 91% variation in my dependent variable voter percentage. Typically, the multiple R squared value for real data, for real applications, may be like 0.75 or 0.6. If you're lucky, 0.8. So don't be surprised if your multiple R squared value turns out to be quite small. It's up to us as statisticians to make a choice and pass a model. For example, there's a possibility that for my given data set, a model that has multiple R squared equal to 40% is the best that I can do. And I have to live with that. Just that I have to admit the fact that this model is going to explain only 40% of the variation in the dependent variable with respect to independent variables. So please make such honest disclaimers when you sell your models to others. Okay, now the last step is to predict what the voter percentage is going to be like if my TV expenditure is equal to 50. And I can predict it in this way. The coefficient is 1.176 696 times the TV expenditure is 50, so that's going to be 58.848. So that's going to be the percentage voters if my TV expenditure is equal to 50. So this is an example of the application of simple linear regression. I can also perform multiple linear regression as well, where I have multiple independent variables. In such a case, I will fit a linear model that looks something like this. LM fit is equal to LM, y is a function of variable x1 plus x2 plus x3. So this is going to fit a linear relationship of y with respect to x1, x2, and x3. So this model will be y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. I can also fit a nonlinear model as well. For example, for some reason, I want to fit, let's say, a relationship between voters and TV expenditure as voter is equal to TV expenditure plus TV expenditure squared. Then I can create another variable TV expenditure squared and set it to TV expenditure times TV expenditure. So that's my another random variable. Next, I can fit a linear model between both my dependent variable and TV expenditure plus TV exp squared. So this is going to give me an intercept value beta naught and individual coefficients for TV exp and TV exp2 variables. Oops. I forgot to include the LM function call here. So that's the LM function call. And if I were to summarize, this is the model summary. In this case, that model clearly does not make sense, but this is just for illustration purposes here only as to how we can still perform multiple regression using multiple variables. So that's the intercept beta naught. This is the coefficient for the variable TV exp, and this is the coefficient for the variable TV exp2. So if I were to predict vote for TV exp equal to 50, this is how I can use the model. 9.656 plus, which is the intercept, plus 0.75 times 50 plus 0.005746 times 50 times 50, because TV exp2 is TV exp squared. So the voter percentage comes out to be 61.5%. I won't be using this model because this model fails on all accounts. Specifically, it fails the significance of individual coefficients, individual regression coefficients. I mean, the probabilities are quite high that these coefficients are in fact equal to 0. They are 56%, 43%, and 65%. So your model fails, this particular model fails right here itself. But this was just for an illustration as to how you can still perform multiple regression. In our class on Tuesday, we are going to solve problem number 14.3, which is an excellent example of multiple regression. I think it's a good time to stop this video right here.